Okay, good afternoon, everybody. My name is Jack Beuth. I'm a professor at Carnegie Mellon University, and let me share my screen, and I'll start into my talk. Yes, what I want to talk about today is some work we've just developed over the past year related to controlling heat buildup and controlling melt pool dimensions through what we call a powder moat scan strategy. And in fact, this is work that two of my PhD students, Evan Dewald and Christian Gobert, have been working on. And this is part of a fairly large project, a NASA University Leadership Initiative program, obviously funded by NASA. It relates to additive manufacturing process qualification. Yeah, so what I want to talk about is a problem I think we all sort of recognize exists, but maybe not to the extent that we have seen, since we've been looking at quite a few high-speed images, videos of melt pools. The issue is really if you're trying to control properties, whether it's trying to control microstructure or trying to control porosity. What you want to do is control um, uh, the thermal fields as you build up a part. And you can sort of decompose this into two effects. One is that as you're building up layer by layer, you can get, it's usually very slow heat buildup or cool down as a function of the Z height in your part as you're building up. Another way you can think about it is that within individual layers, as you're doing fill patterns, and we'll look at raster fills, you can get within each layer then local hot spots or local heat buildup as you're filling in a layer. What this talk will address is the second problem, local hotspots within layers. There are ways to approach the second problem as well. And the idea is if you cover both of these, then you will get consistent melt pool dimensions. You will not build up a thermal field, a high temperature field around the melt pool, which could um, alter microstructure or porosity, even if you control the melt pool dimensions. And if you cover both of these, then you can perform, say, single bead tests or single bead simulations. In fact, we do this all the time. And we take melt pool dimensions from those single bead tests and we use those to plan out process parameters for different alloy systems. If you cover these two thermal control issues, then that allows you to consistently then use those single bead dimensions with confidence as you are building up layers and as you're building up a part. They actually they remain relevant throughout a build. So what we'll do is we'll talk about scanning strategies. I'll go through just standard rasters and contours, and then what we call the powder moat strategy, which is um, a, a new version uh, of, of raster patterns. Then I'll show some results, high-speed imaging results. So the big point here is that if we use this powder moat strategy, and you can use it on any machine, you will get much more consistent melt pools during a raster fill. And essentially it solves the second problem, which is the local hotspot problem. And I'll give a little summary at the end. So I mentioned before that this work it's actually part of a NASA University Leadership Initiative program on additive process qualification. And what that program, the goal of it is to base process qualification first on controlling porosity. Um, and that's done by identifying a process window. So the window here is in green. And if you are within that process window and you're not up in the upper left-hand corner where you get potential keyhole formation of keyholing pores, and you're also not on the lower right-hand side of the beam power versus beam travel speed plot, where lack of fusion occurs, you'll be in the processing window, you'll avoid key holding type flaws and lack of fusion type flaws, and you would hope to get consistent and good results for fatigue lives within this window. Um, and I won't go into too much detail about this. I don't want to spend too much time on the process window concepts here, but the idea is actually you can manipulate where these boundaries are. You can manipulate them on the bottom end based on um, by changing a layer thickness and also hatch spacing, and you can manipulate them on the top end by changing beam focus or the effective spot size or spot diameter. Um, so this window is not fixed. It can be controlled by other parameters. Well, so the point is we are performing experiments, fabricating fatigue specimens for process parameters both within the processing window and outside the processing window. And ultimately, the goal of that project is to start to map out um, uh, curves of constant fatigue life uh, in sort of a PV type space. And the point is that if you have the problem, back to the subject of the real talk, if you have the problem of local heat buildup, then that can be a significant source of variability in the fatigue lives. Now, we haven't shown that specifically, but obviously, if you have heat buildup, it could, for instance, if you think you're in the processing window, it could actually trigger, for instance, key holding flaws, even though you don't expect them. And so it's certainly a potential source of variability in specimens. And um, yeah, and not only that, it can also cause different results for different sizes of specimens. So in fact, everybody likes to test fatigue specimens that are subsized because you can get more tests in. Um, if you don't control the thermal conditions as you build, then it's very much possible that the results you get from small specimens would not be comparable to results you get from large specimens because you can get more heat buildup in the smaller specimens. And other fatigue studies have, as far as we know, have generally ignored this problem or this potential problem. And so we were seeing this and thought about how we could address it. So just to give you a sense of what we're talking about here, this is some earlier work. In fact, this is a video by one of my students, Nick Jones, which is a high-speed video image of filling in it's 4 millimeter by 6 millimeter rectangle. And what's been done is the melt pool boundary has been designated here by the red lines. And I'll go right back to the very beginning. When you first start out your raster pattern, you have fairly short raster lines, and you can get some melt pools that do not look like the melt pools that you get in the middle of the raster lines. Show that. Uh, once the raster lines are long enough. So if you look at what's going on here, the melt pool, once it's in the middle of the block, obtains a pretty much steady state melt pool size and shape. And you don't get the local heat buildup you got at the beginning of the rasters. Another issue is that actually when you stop and turn around and come back, the melt pool is a little bit fatter and has a little bit longer tail than what it does in the steady state condition. And that's because it's turning around and coming back right on top of material that's been heated by the previous laser pass. And then what happens when you approach a corner is you actually get significant heat buildup in this corner, and the raster lines get shorter and shorter. And so now you're really just getting a blob of melted material. And that is the melt pool as that raster finishes. And now here comes the contour. Actually, this contour even gets perturbed. That melt pool gets perturbed to some extent by going through this hot spot. And again, this is a real concern for fatigue because you are now putting inconsistent melt pools with inconsistent structures, potentially inconsistent structures, right near the free edges, which is the key region where you want to control things optimally. So we had seen this I guess this is probably about 2.5 years old when we first got our high-speed camera. And we recognized this problem. And once we got into the NASA ULI program, became clear that we needed to address this. So let's move on. Yeah, so the way we addressed it is this. So in fact, in all the cases I'll show here, we will do raster fills across um, uh, the entire cross section. What we'll be looking at is in this program, we're doing bend fatigue specimens. They are 6 millimeters by 6 millimeters in dimension. And so we'll be rastering across those. We do use the EO, this is on an EOS machine, so we do use the EOS standard of rotating 67 degrees after each layer is deposited. Um, and just as what we showed you actually from those high-speed image results, you'll get heat buildup here. You get heat buildups at the end, heat buildup at the ends of the rasters. Plus, you get heat buildup, particularly when you're finishing up at the end. It happens for every single layer, and it doesn't have to be a square, and it doesn't have to have corners. As long as you get reduced raster lines at the end, which you always do, this problem presents itself. So the approach for this is our powder moat strategy, where we're depositing the same cross section. However, we're also depositing a sacrificial thin wall, a prescribed distance from that cross section, all the way around the cross sectional shape. And in fact, we'll be doing um, square specimen dimensions here in this talk, but the strategy applies even if you have an arbitrary shape for your individual layer. And the point is what we do is we force the laser as it comes to the end of the part to jump over to the wall, do its turning around out here on the wall, and then come back and hit the part. And the idea is that we choose this. So this is a wall, this is the part, and there's a powder moat in between, which is not fused. That's the moat part. And so we choose the width of the moat such that when you come back, the part has cooled enough so that it will not change the melt pool dimensions. Okay. Yeah, and in fact, this is really not originally our idea. In fact, there's a project I had with University of Texas, El Paso, geez, more than a decade ago, and it was Ryan Wicker, and some of his students were working on that project, and they were doing work like this, and they had just observed that they seemed to get more consistent results if they built these walls around their specimens, although they didn't have the high-speed imaging capabilities to really tell them what was going on. They just observed that it seemed to help out. So I've got to give credit to Ryan and his group. Yeah, so once again, you'll see builds where we are building a square cross section. That's the part. The region in between is the powder moat, and then we have a thin wall out here. Those walls are 1 millimeter thick, but they don't have to be even that thick. They just have to be substantial enough that, for instance, if the recoater blade comes over and hits the wall, that it doesn't mess up the wall. So the dimensions of the wall itself really aren't important. And once again, and so for what I'll present today, we are making it so the delay when a raster comes to the end of the part, the delay in going out to the wall and coming back is at least enough to make it so that uh, um, um, you're simulating the longest raster line in filling this geometry, which is one that goes from corner to corner. Since we did this work, we now have very methodical criteria for either the delay times that you have to put in at the end of each raster line, and we've done it for TIE 6.4 at this point, um, or the widths of the moat. Okay, so this is a variable you can set as a function of process parameters. We've got a paper that we're about to submit on that, and so that will be out pretty soon. Just to give you a sense of what the experiments are, and I'll show some videos here, and I think everything will start to make sense. What we're doing is you can do a lot of different parameter sets, and you can do that with walls and without walls, just with a single block. And what we're doing here is we do one parameter set for 10 layers. And in one of those layers, we then take the high-speed images. What you can do is do this all with one block and first do your wall builds, and then stop those, and then just do the cases without walls and build up. And so there are lots of cases that we've covered. In fact, they really cover this entire parameter space here. And I'll just show a couple of them for illustration, but we've mapped this out quite well. We're using a high-speed camera mounted on the top of our EOS machine. This is one of the top viewports. Uh, um, the field of view is just a little bit bigger than the 6mm by 6mm specimen that we're depositing. We can, at this resolution and at 6,400 frames per second, with the current storage in the camera, we can go for, it's really less than 2 seconds to fill, but that's enough to fill this full 6 by 6mm space. Okay, so now some fun stuff. We'll show some movies. So first of all, this is with the EOS nominal settings for TIE 6.4. And again, no wall in this case. And we're going to do a full raster of the area. And we haven't outlined the melt pool, but it's roughly what you see glowing. Actually, what you see glowing is a little bit more than what the melt pool is. So let's go back to where we were. And so these results, let's go back to where we started. These results are analogous to what I already showed you, okay? Although it's specifically for the geometries we're looking at in the program. Yeah, so here, initially melt pool that is not very well consistently shaped, and it is bigger than what it is once you get to the middle of the specimen and you start to get nice steady state melt pools in the middle. Uh, you do see splats coming out of the melt pool. In fact, we have a project where we are quantifying those splats that are coming out of the melt pool. What you also see is that you get to the end and you turn around and come back, and it's somewhat subtle for these settings, but it is there, that initially the melt pool is a little bit bigger and fatter than what it is once you get, make sure we're here. Come on. Once you get in the middle of the cross section. Yeah, and it's also true, you can sort of see that the melt pool length, it's a little bit longer there right at the beginning until it gets out of that local hot spot and reaches a steady state. So again, heat buildup here, heat buildup somewhat at the ends of each of the rasters, and then as you come into this corner, we'll let it go. You can see the melt pool's getting a little longer there. You get this local concentration of heat. Not too bad, but it's definitely there. Whereas the next case, so what we're trying to do in this program is sort of break out of just the standard parameters, which are in the processing window, um, break out and look at a range of parameter sets and power velocity combinations. And what happens if you are in the, for the spot size that we have, that we are in the keyholing regime. So now this is the most severe case of the ones we looked at. So here you have a lower travel speed, you can see that, and essentially the same power, but here you get significant heat buildup in the upper right-hand corner. The effects that you see at the ends of the rasters are more exaggerated. Again, a longer melt pool length plus a fatter melt pool at the very beginning, so that would be the melt pool width. But still, once you get in the middle of even this pretty small part, 6mm by 6mm, you do reach a steady state. Those are nice melt pools there in the middle. And one more time, what you're trying to do, what you would like to do is have it so you get those melt pools, uh, even at the ends of the rasters and even at the beginning and at the end. And I'll skip ahead a little bit here just to save some time. As we approach the corner here, in fact, you can already see there's a problem. That melt pool stretching all the way across the width of the specimen. And it is now one big glowing blob. And again, clearly in here, you're going to have different microstructure formation, lower cooling rates, for instance. Also, the potential of formation of keyhole porosity if you are not getting it already. That's what you get without walls. Okay, so now we'll look at this one worst case. And like I say, we looked at many cases, but for the sake of time, we're just going to show this one. So this is that same keyholing case. So we're in this region of the PV plot, but now we include the wall and the moat. Okay, so we come to the end, we stop. Now, actually, that laser's going out to the wall. The wall's out over here, and it's turned around and come back. And so what you see is that two things have happened. You didn't see the big blob at the beginning. And now even when the laser comes back after the end of a raster, it very quickly develops this. In fact, it almost pretty much just does develop the correct melt pool dimensions. In fact, the width of the melt pool is about right. And also, as soon as it goes far enough to develop its tail, the length of the melt pool is right. Okay, and I'll move a little faster here. So if you remember from the prior video, once we were here, we were getting, melt pools extending across the whole cross section, starting to get a big blob, and now we are not getting that. And in fact, again, this was not with totally optimized moat widths, but you can see that we're doing pretty well in filling in even these little short regions, these short raster lines, right to the very tip end of the square cross section. I think it comes back one more time. There it is. Okay, so that's the idea. And again, we studied this over a range of parameter sets, and this is for TI-64, and the strategy works. You may have noticed that that build took longer to execute than the one in the prior, that layer took longer to execute than the one in the prior video. And this does add time to your build time, although that's easily quantifiable. I'll talk about that on the last slide. So literally for this project, we are doing just cross-sectional shapes, and these are specimens that we section, and we are building the walls and the moats around them. And then, like I said, we are doing 4-point bending fatigue specimens. In fact, that's work that's being done with John Lewandowski at Case Western University. And in fact, also, there are other universities. University of Pittsburgh is part of this project, also University of Texas at El Paso. Also, Worcester Polytechnic Institute is part of this project. Anyway, back to this. So we are building the bend fatigue specimens with the walls and the moats around them. And we are in the process of doing head-to-head comparisons now between specimens that are fabricated with and without moats. So let me sum up. Okay, so I talked about two problems, heat buildup type problems in a build. One is as a function as you build up the whole part, which we did not address in this talk. The other one is local hotspots as you're filling in an individual layer. And then for those hotspots, there are really two issues. One is just the ends of all the rasters, they're still hot when the next raster line begins. So you get a local change in melt pool dimensions then. And then when the raster lines get short, you get heat buildup there. This also occurs if you use the EOS strategy of stripes, for instance. And in fact, it's worse because it happens at the end of every stripe as you're filling it in. If you apply these moats, then you can address both of these problems with respect to hotspots in a very well-defined way. The strategy we laid out can be applied to any additive machine. Now, it is true that some machines now do allow users, I think it's just maybe a couple manufacturers, allow users to specify a delay time at the end of each of their raster lines. And if you do that, then you do not have to build the moats and the walls. However, you need to know what those delay times are. And so we've mapped those out as well. And that will be coming out in the paper in a couple of months. Build times will increase, but the rule of thumb, it's not quite accurate. The rule of thumb is if you're looking at the ratio of the part and the part plus wall areas, um, then that gives you a guide as to how much longer it's going to take you to build with the walls, because you're having to raster all the way out to the walls instead of just to the edges of the part. Like I say, we've already worked out now these moat widths and also delay times at the ends of rasters across parameter space for TIE 6.4. And again, we're moving along to really test not just the way the melt pools appear, but also fatigue properties as a function of using these moats and for not using them. And if you have any questions or concerns, you can contact my students, Evan or Christian, or you can contact me. These are our email addresses. And I thank everybody for their time. And let me do this and that. Okay, goodbye.